As we know, a charge can experience an electrostatic force due to the presence of other charges. For instance, the positive charge Q0 experiences a force, which is the vector sum of the forces exerted by the charges on the rod and the two spheres. It is useful to think of Q0 as a test charge for determining the extent to which the surrounding charges generate a force. By calling it a test charge, we just mean that its magnitude is small enough that it doesn't alter the locations of the other charges. We can move this tiny test charge around these other charge distributions to sort of map out the electrostatic forces in the surrounding area. For instance, here, the negatively charged sphere attracts the test charge and the positive sphere repels it. Also, the negatively charged rod certainly has some attractive effect, but it's farther away, and we know that the force will weaken with distance. The resultant force, the vector sum of all of them, would be in the direction of the blue arrow. In this case, the rod and the negative sphere would both attract the charge relatively strongly and, to a weaker extent, the positive sphere would repel it. Note that the attraction from the rod and the negative sphere would have a partial canceling effect, and the net force would point along the blue arrow. Here, the negative charge distributions both have components that tend to pull the charge toward the point between them with a force that is stronger than the attractive force from the positive sphere, which is located at a greater distance from the test charge. It's only a qualitative description, but you should get the idea. Using this little test charge, we could map out the entire region around the charge distributions and give the direction and magnitude of the force at every point. Once that was done, we could hide all of the charge distributions and forget about them, because we would know how the test charge would behave no matter where we put it. Now, what if we place the test charge in its initial position and then double or triple its magnitude? We know that as long as the test charge doesn't alter anything, the force it experiences will also double or triple. But then we'd have to change our force map. We'd have to multiply all of the values by 2 or 3, or by whatever the magnitude of our test charge is, to get the correct value. But what if we instead mapped out the force per unit charge, rather than just the force? Then we could place the test charge on the map and just multiply it by the value of the force per unit charge at that point on the map. This is precisely the origin of the concept of electric field. The electric field that exists at a point is the electrostatic force experienced by a small test charge, Q0, placed at that point, divided by the magnitude of the charge itself, or E equals F divided by Q0. The electric field is a vector, and its direction is the same as the direction of the force on a positive test charge. The SI unit of electric field is the Newton per Coulomb. Just like the force on a test charge, it is the surrounding charges that create an electric field at a given point. The electric field gives us a mapping of the values of the force per unit charge at every given point. Once we have that knowledge, we don't care much about the charge distributions that created the map. Let's see how this works in a simple case. Suppose that our previous charge distribution, the charged rod and spheres, leads to a point P with an electric field that has a direction of the blue arrow and with magnitude E equals 3 newtons per coulomb. Remember, the electric field is a vector. What is the magnitude of the force on a charge Q1 equals 12 times 10 to the negative 8 coulombs placed at point P? We start with our definition of electric field. We can work with magnitudes since that's the question, and we write E equals F divided by Q. Note that we just replaced Q0, our test charge, by Q. From this point forward, we will always assume that the charges for which we calculate the force do not alter the charge distributions creating the electric field. Now, solving this for the force, we have F equals Q times E. This is a form of the equation to remember. Just multiply the charge by the field to get the force. This is equal to 12 times 10 to the negative 8 coulombs times 3.0 newtons per coulomb. The coulombs cancel, and we are left with F equals 36 times 10 to the negative 8 newtons. Since the charge is positive, the force is in the same direction as the field. Now let's instead place Q1 equal to negative 8.0 times 10 to the negative 8 coulombs at point P. We know immediately that the negative charge means the direction of the force will be opposite the field. But let's calculate the magnitude. F equals Q times E, which equals 8 times 10 to the negative 8 coulombs times 3.0 newtons per coulomb, which equals 24 times 10 to the negative 8 newtons. Again, this is just the magnitude. The actual force points in the direction of the green arrow, in that from the positive charge along the red arrow. Suppose we were given the individual contributions from each of the charge distributions, the rod and two spheres, to the total electric field at point P. How would we get the total electric field at P? The answer is that, since the electric field is a vector, we would just add them like vectors. In this case, we just showed the addition graphically using the tail-to-head method. However, you will find yourself having to use all of the vector tools in your arsenal to find components, angles, etc. The electric field produced by a point charge q can be obtained in general terms, meaning as an equation, from Coulomb's law. First, note that the magnitude of the force exerted by the charge q on a test charge q0 is F equals k q q0 divided by r squared, where we have just replaced q1 by q and q2 by q0 in Coulomb's law. Then, divide this value by q0 to obtain the magnitude of the field. Since q0 is eliminated algebraically from the result, the electric field does not depend on the test charge. We have E equals kq divided by r squared. The direction of the electric field is always directed radially inward or outward from a point charge. Imagine placing a positive test charge near a positive point charge. No matter where you place it, the force would be repulsive and radially outward. Note also, the magnitude of the field drops off fast, as the square of the distance r from the source charge. Now imagine doing the same thing for a negative point charge. Your positive test charge would be attracted to it, radially inward, no matter where you placed it. The radial lines we've drawn here are called electric field lines, something we'll discuss in greater detail in the next section. Our equation for the electric field of a point charge is a very useful result. With the aid of integral calculus, this equation can be applied in a variety of situations where point charges are distributed over one or more surfaces. One such example that has considerable practical importance is the parallel plate capacitor. As seen here, this device consists of two parallel metal plates, each with area A. A charge plus Q is spread uniformly over one plate, while a charge negative Q is spread uniformly over the other plate. Imagine placing a positive test charge between the plates. The force on the test charge clearly points away from the positive plate and toward the negative plate. In fact, everywhere in the region between the plates and away from the edges, the electric field points from the positive plate toward the negative plate and is perpendicular to both. It can be shown that this electric field has a magnitude of E equal Q divided by epsilon naught A, equal to sigma divided by epsilon naught, where epsilon naught is the permittivity of free space. In this expression, the Greek symbol sigma denotes the charge per unit area. Sigma equals Q divided by A, and is sometimes called the charge density. Except in the region near the edges, the field has the same value at all places between the plates. The field does not depend on the distance from the charges, in distinct contrast to the field created by an isolated point charge. In summary, the electric field that exists at a point is the electrostatic force experienced by a small test charge q0 placed at that point divided by the charge itself, or E equals F divided by q0. The electric field is a vector, and its direction is the same as the direction of the force on a positive test charge. The SI unit of electric field is the Newton per Coulomb. Finally, the electric field of a point charge is E equals kq divided by r squared, and is directed radially inward or outward.